Okay, so can anybody see this, my screen share on my browser?
Yes.
Yeah, okay,
Yes.
good. So I think there's a bit of confusion here, so that's fine. I'm going to, because it's the first one, so I'm going to extend it. And instead of it just extending to the end of the day, I'll extend it to next Friday. That's fine. So then I'll go through the solutions with you next week. So remember last week we had sort of a very quick sort of trial about what the quiz will be like and so on and so forth. The idea was that I wanted to show you, if you go to sort of the content page, right? You should be able to see like the material for week 1 and then week 2 and so on and so forth. Does everybody see that? Right. So if you go to week 1, then if you click on the first page, right, then you should be able to see that, oh, there's a lab exercise, right, that I want you guys to work on. Okay. And then when we were going through it, I said, okay, you know what, we're going to try this. And I showed you what the questions were. So if you go back, right, we're able to click on page 2. And then I said, oh, I would like you guys to just sort of work on these problems and then get it submitted. So maybe that wasn't the clearest. So what I've done is, okay, so there's only just really these questions, 1, 2, and then 3. Okay. Even though it was not a quiz, but I did want you to just practice just to see where you are at in terms of comfort level with logs. Okay. So what I've done is I've gone ahead and go to assignments. So everything is submitted through the assignments. I guess you can see it, but I've extended it. Oh, hold on. I did the end date, but I did not change the. So if I go to the 15th. Okay, so for a one-time sort of a thing, what I've done is I've made this now due right on the 15th. Okay, because there was about 12 of you that did not submit it across the 2 morning and afternoon sets. So I did not cross-check the name list, but I assume roughly five from each set. Is that clear what you need to do? On the content page, could you please make posts on the content page? Sometimes things aren't clear. Oh, okay. Don't worry about it. This is the only one that you would do it as for deliverable next week. This is the only one. Everything else will be due in class because it's the quizzes and stuff like that. And because maybe there was a big confusion with that, I went through with you guys, but I did not. Maybe I may not have been the most clear, saying that you have to get it done by next Friday. But this is where it will be done. So if you go back to your home page, okay, and I can load this up. You should see now for the 15th, this is what this is due. Does everybody see this? You click on it, right? This is the one that's due by May 15th. Is that clear, Chantal? Okay, so what is this one? So I just want you guys to go back and work on it. It's a practice anyways, but I do want you to work on it so that you get a quick assessment on how well you are with your sort of quizzes, your familiarity with logs, and so on and so forth. Okay. Okay, so remember, so today we're going to start with, I'm going to just sort of mute everybody here for a minute here. Okay, there's a bit of background noise. Okay, so today what we're going to do is we're going to go through a full class today, so sort of a little differently than last week, okay? Yeah, so let me just respond to this. Yes, you can, you know. Okay. As I said, this is an exercise that I want you to work on that is just, sorry, just responding to public, that is just a practice for you. So it's not really counted as a quiz, but it's a practice that I want you to just work on and go from there. Okay, so today, what I plan to do with the time is that I want to go through a regular class, okay? So the lecture material of this is posted. We did not finish module 1, then I'll do that. And then what we'll do today is we'll do a mock quiz. Okay, which means I'll run it like a quiz, but you will not be penalized for the quiz. So it will still be graded, but it's just that I want you to get through the process like an actual quiz. Okay, and then we'll do that after we do sort of the review. Okay, so let me get the deck of slides up. Are there any questions from anyone? Any questions from anyone at all from the material? Oh yeah, don't worry. The quiz, Edward, probably won't start until maybe close to 10 o'clock. Okay. Usually, what I do is I do a review with everybody before I start to go through that. Okay. Any questions? Are there any questions at all from anybody? From the material from last week? Any sort of the logistical issues for the course at all? So the only one thing that I think we didn't catch on is obviously submission of the lab exercise 1. Today, what we'll do is we'll go through a review of the material and then complete chapter 1, this module. We'll do the mock quiz, right? So the mock quiz will be done in a way whereby I will facilitate it like the quiz. But I suspect that there will be some glitches in terms of the submission, so I'm not going to count it towards marks, but I'll grade it. So I'll give you more than enough time to sort of get it submitted, but it will not count towards your marks. Okay. So for those that did not submit the first lab exercise, please do so by next Friday. Okay. If there are no questions, then I want to sort of get on with the material. Okay, and go from there, and then I'll take the questions as necessary. So as long as there are no sort of logistical questions with the course, welcome everybody to week 2, right? Just so you know, there's only 12 weeks in this course. So if you're in week 2, right, you are about, at the end of today, we'll be 1/6 through the course, right? So the course progressed quite quick. There is a string of very good weather. Please do enjoy the weather. I know after the class, right? So if you want to do that, right, feel free to do so. But at the same time, please make sure that you abide by all public health advisories in terms of social distancing and so on and so forth. Okay, so let's just get started, and then we'll see if we can do the mock quiz in a bit. Okay, so last week I gave you a very quick overview in terms of the course, right? The idea was that we spent quite a bit of time trying to show you what the roadmap of the course is, sort of try to go through sort of the ideas of what the future sort of developments in this field will be. That's essentially because I want to be able to sort of allow you to get a view of what's expected of you from this course in itself and what's expected of you from the material itself. Right, and my motivation was very simple. I wanted you to be aware of, if anything, of what and how it applies to the particular options that you might choose to get into next term. Okay. So when we first started, right, we said this, right? Data communications is not networking. Right, it is actually quite different in terms of the content that we'll go through, where in most cases what we care about, at least for the first half of the course, is the transmission of a single bit. So we're not going to be looking at routers and switches, and so we'll do that after 5 weeks. The first part of it, right, is probably the most difficult for the students because we go to the physical layer where we look at how every single bit gets transmitted. Okay, it requires you to have some knowledge of sine waves, right, which we will do a review of as we sort of go through the course. But many students, after going through sort of the first 5 weeks of the course, actually, while they might find it somewhat more difficult, ends up getting a very deeper appreciation, actually, of data communications, which is something secondary that I want you to be able to achieve. So why do we do this? Because we want to share information, right? My motivation to you was that if you look at all of the applications that you do, if you look at all of the work that you do on networks, it is very, very unlikely, right, that you're dealing with the data that's actually local. which means, right, you're sharing mostly now, right, in today's context, the data to be remote. You're dealing with somebody, right, where you want to now transmit. And the remote could be within the same network in terms of a single broadcast domain, right? Or it could be across sort of multiple networks, and it could be as far as thousands of kilometers away. Okay, this is what we call telecommunication, right? Because we want to share information very much at a distance, right? Across some medium. Okay, is that clear?
So far, yes.
Okay, then we said this. Well, there is a minimum of 4 components, right? Where the first entity within this communication network is that obviously you have a sender, right? Somebody has to initiate that information transfer. Somebody has to receive it. That's the second entity. And we know that we need to have some kind of transmission medium. Okay. If this was an in-person class, right, the transmission medium will purely be the air between us, right? So the air is a transmission medium, right? Wireless signals goes through that as in the form of sine waves. But obviously, we want to have the fourth component, the information content. Right, this will suffice. Right, this will allow us to have some kind of communication, a sender, receiver, some medium, and obviously the intended message. And the message can be anything. It can be text, it can be video, it can be some kind of a stream. It doesn't really matter. But what then we also motivated was that there is a fifth component, right, that is now in fact a requirement because we need the communication to be very efficient. Right, the idea, the motivation was very simple. How many packets of information do you think, right, it is being transmitted across networks on a daily basis? And the answer is very simple, right? It's probably in the trillions. So one counterexample that I gave you was if I were to try to go and buy hamburger in Russia and I don't speak Russian, I probably will get what I want at the end of the day, but I probably would have to spend quite a bit of time trying to illustrate exactly, especially if I'm trying to customize my burger. Okay, so the motivation is very simple. We need these protocols because we want the communication to be efficient. But more so, if you recall, is that I also said that we want this communication, right, to be interoperable between different manufacturers of devices. And if you look at all of the devices that you use to gain access to this course, the equipment that you use could be made from Apple, could be made from Dell, could be made from Lenovo, et cetera, right? It is one thing, right, to be able to communicate, but it's different when you want to communicate efficiently, right, across manufacturers, different manufacturers of the equipment. Okay, so this is the basis, right, in terms of what the 5 components are in sort of modern day communications and what we call telecommunication, which is across a distance. Okay. Any questions? So this doesn't just pertain really just to communication between sort of 2 individuals, right, or 2 computers at 2 different locations. If you start looking at this type of communication, even sort of transferring files out of your laptop, right, onto say an external USB drive is exactly the same thing, right? The transmission in this case obviously is a USB cable. Right, the information content, right, is the bits that are going, right, and the protocols because you're abiding by USB's transmission standards, right, and so on and so forth. Okay, so that distance doesn't have to be very large. It could just be obviously, right, from the SSD on your laptop, right, transferring out across a USB cable to a external drive. Okay, please stop me if you have any questions because this is all just review. So I want to just sort of pace through it. Then we went on and we said, you know what, communication in terms of data flow, right, can take on 3 different types of mechanisms, right? There is simplex, where all it is that there's only one single direction of flow. And you cannot change that, which means the data only flows only from the sender to the receiver. Okay, from the sender to the receiver. What I mean by that is that there is one data that's coming out, okay, and then there's one receiver that's receiving it. In the case of a keyboard, for example, the sender is always the keyboard, right? The receiver is always, right, going to be sort of the motherboard. So that's simplex. Directionally, it's only one direction, and you cannot change that. But most cases, right, what we want to have bidirectional communication, which means obviously there's data going back and forth, right? Information content being shared back and forth in both directions. We can achieve that in 2 modes. Okay, the first mode is what we call half duplex, where the idea is that data only flows in one direction at a time, but you can reverse that direction at the next moment in time. Okay, a very classic example of that is walkie-talkies. Okay, a walkie-talkie says this: if somebody wants to talk at any moment in time, only one person can be sending, but you can have bi-directional flow of data, which means that A talks, B listens, B talks, A listens. Okay, the benefit of these two, right, both simplex and half duplex, is that because only one user is transmitting at any moment in time, right, the user actually gets the entire capacity of the channel. Okay, the third mode, right, called the full duplex mode, right, is whereby now you can have simultaneous bidirectional transfer of data. Okay, simultaneous means at the same time. So if I were to talk now, right, and Rana talks at the same time, right, Rana, can you say a few words while I'm talking?
Yes, certainly.
Yeah, exactly. So does everybody hear that, right? So she's talking and I'm talking, right? Effectively, right, we're using the channel at the same time. So we don't have to take turns. We're just talking at the same time. The information is going back and forth. The most common example of such a flow of full duplex, right, is the telephone network, right? Sometimes you would talk at the same time. Not very efficient, I would argue, right? Depending. But most bidirectional simultaneous full duplex machines have dual, what we call transceivers, meaning that you are transmitting and receiving actually on two different channels, so that the information is not sort of barged in at the same time where it interferes. Okay. Now, the issue with this is that, yes, I've achieved simultaneous bidirectional communication, but obviously I need to allocate certain amount of capacity to each of these channels, right? So you're sort of sharing that. And the sharing, as I said, does not have to be 50-50 in terms of sharing. Okay. Chantal, I don't really know what you mean by videos that illustrate data flow. It just means that there's a stream of bits that goes from one sender to the receiver, either only in one direction, in both directions, but taking times, right? Or simultaneous in both directions. And the other thing that I should note is that your sort of understanding of this, right, minimally out of this slide, is really just the classification in terms of terminologies of simplex, half duplex, and full duplex. Okay, you can just imagine data is actually flowing just one direction. So I don't know if there's any videos that are made of this, because it's simply a concept of us and how we actually allow directional flow of data. Okay. Okay, so then we started off, and then we went on and said, okay, well, in the context of a network, right, of what we usually have, what we now want to say is that we could send, oops. So in the context of a network, right, what we have now is this, is that we have more than two entities on the network. So we might have one sender, one receiver, but we have many other sort of intermediary nodes in between, like switches and routers, and perhaps also many other devices on the networks that are also trying to communicate at the same time. Okay, so what we have now is not just a single communication channel between two entities, right? But we have many other devices, and they take on different purposes, right? So you can imagine a home network, right? You have a network printer, a network drive. You could have your streaming devices, such as an Apple TV, right? Or Chromecast, right? Et cetera, et cetera. Now, what we want to be able to show is that this is the type of network where we deploy these devices. We now need to be able to determine performance in such a network, which obviously is more complex than having just two simple entities. Okay, the criteria sort of that I laid out last week, right, simply says this: we as an end user only care about performance, right? And performance also very sort of in a very specific way is that we want a very high throughput and a very low latency. So you might be able to recall that I said that, right? If I poll all of you here, what is it that you want from your network provider, right? The top two responses among others might really be, I want the highest possible data rate, with the least amount of delays experienced through the network. Okay. But from a network service provider point of view, and that was what I was trying to motivate for you guys, is that while that may not be, right, the only concern for the service providers, because they also care about the reliability of the network. Not that you don't, but it is the responsibility, right, of the network providers to ensure that there's reliability on networks so that the networks are not always going down. And what does that mean? Well, reliability from a metric point of view, so a measurement point of view, right, is really a measure of how frequent the network fails, right? But it's more than just that about failing, but in the event that it does fail, right, how quickly it can actually recover. Okay? And obviously, right, you want to make sure that you build your networks as robust as possible so that the actual downtime, right, or the frequency of it fails, right, is kept to a minimum. And obviously, the one thing that is on everybody's mind is security as well, right? To end user, the security may just be a simple username, password, but that's really just an authentication part of things. You're just really identifying who you really are, right? Networks care a lot more than just that in terms of authentication because they want to actually protect the data. But at the same time is that if we know that there will always be security breaches, then what we really want to be able to do, right, is how then do we recover? So if you think about the classic sort of breaks of networks, say for Live Labs, for example, right, that happened and hit BC a couple of months ago, right, where millions, I believe, right, of sort of test results and accounts were sort of compromised. In that particular case, I believe they paid their way out. But the question really is this, is that how do you have policies and detection mechanisms, right, to even know that your network, right, was in fact compromised? Okay, so those are the three sort of key things. To the end user, mainly your consideration has always been performance, right? And I'm talking about the average end user, right, like your grandparents and so on and so forth, right, your little brothers and sisters. But to a network service provider, and you'll see that throughout this course, we put a lot of emphasis on the network service provider because at some point when you graduate and if you go and start working, you will likely be working for a service provider than for an end user. Okay, and obviously the considerations by all of these service providers, right, is one that you should take note of. Okay, I believe this is sort of where we stopped last class. And I'm going to go into the new material. Any questions? Are there any questions at all?
No, we're good.
Good. Okay. Is that clear on what we have covered so far? And again, I said the first two sort of the first lecture of material is very lightweight. It's very much just terminology and sort of laying out sort of the framework of what we're actually going to be studying going forward. Okay, so let's take something a little bit. The reading, right? As I kind of say this is that please, if you guys can, right, make sure that you're at least browsing through the textbook, right? You're not actually reading it, so that you're coming in and getting more sort of explanation. Okay, so I want to go into now topologies, but before I can actually do that, right, and look at the different types of topologies, I want to sort of share with you another two terminologies, right? Simply, the first type of connection that we have is called a point-to-point. Okay, so what this simply means is that there's a dedicated link between two devices, right? So there's A and B and they're trying to communicate, we pull a cable across. Okay, and then obviously because it's a point-to-point link, right, the capacity provided by this link, say it's a USB 3 cable, right, the entire sort of a material. Yes, I did release the material ahead of time, right? I think I did it by Tuesday or Wednesday. Was that right, Rana? Were you aware of that?
Yes, I know, but I mean, can it be really earlier? Maybe if you can release all the reading material like a week or so before, so we can actually swift through them, so we can actually take our time in reading.
Sure. Okay, that's fine. So what I'll do is maybe I'll get them the reading material released after the classes, like by Sunday. Is that okay?
That
so Monday morning.
That would be great.
Yeah, because the reason why I don't release it all, so if you're interested in how we will progress through the course, it's on the course outline in terms of the chapters. But the point-to-point reading, I usually release after the class so that I know how much I covered the previous class. So I do sort of real-time adjustments on that on a week-to-week basis. But the entire course plan in terms of the chapters that you would need to read is actually on the course outline that's published. The actual pointed form of reading is a function of how much we cover on a per class basis. So I adjust that in real time. So I'll do it at the end of the class. So maybe by Monday morning, I'll get the reading material out for you guys. Okay?
Great. And also the extra material, if they can be released so we can, go through them.
Yeah.
Because the theory that was provided, I would like to go through it all. Thing is, I don't have enough time. So maybe.
Right. Okay, that's fine. Okay, so in general, right, get an early release of the material for you guys so that you can prepare for the class next week.
That would be appreciated. Yes.
Yeah. No problem. Okay.
Thanks.
So let's get back to this, right? So sorry, I got interrupted by that. But the first type of link, right, it's a point-to-point, right? So the idea is simple. This, right, is that if I have one link, right, between two devices, it's fully dedicated, it is awesome, the capacity is all mine, this is perfect, right? Security and so on and so forth. But in reality, we don't really do this. Why do you think we don't do this? Why do you think we don't do this? Cost, exactly. And I would argue, right, more than just what Shen Kai has said, that is cost. In fact, it's unfeasible. Now, just imagine, right, from the moment you wake up this morning till now, right, how many websites have you actually visited? Okay, and then look back to the entire week. How many websites have you visited this week? And then look back to your entire lifetime. I'm talking about your entire life to date, right? How many websites have you visited? And if my argument is this, for every website, and different websites, of course, that you've visited, I want you to pull a dedicated point-to-point link between your home computer and the web server. Is that possible? Right? So it's not just cost, it's probably infeasible to do so. And we'll start to see that, yes, there's greatness in point-to-point links, but there are also many sort of issues with point-to-point links, because for one thing, right, it perhaps is not actually very practical. So in real life, right, most deployments, right, is in a multi-point sort of a infrastructure as you see here. Okay, this is a classic sort of like T-junctions where you have a main link, right? And then what you then have is that as machines wants to be added onto the system, right, you just start tapping off. Okay, so what does that mean? Now, all of a sudden, right, you have more than two devices sharing the single link, right? In fact, you start to see that the hubs that you use, right, are all of these sort of this nature, right? And more so is that now you're sharing capacity. And then there obviously is degraded security. Right. Obviously, this is not optimal if the data that you require, right, it requires to be highly secure, right? But this is the more feasible deployment mechanism, because now you are sharing, which is a great thing because you don't have to have dedicated links that we argued in point-to-point was infeasible. Okay, so right. So I was trying to follow the conversation between Edward and Chantel, but just so you know, right, this point-to-point, right, was awesome. Okay, this is what we would like to have. Okay, but it's not practical. So in most cases, right, what we do is we deploy this. So if you go around SE12 in BCIT, right, Bernabé Labs, right, they're all multi-points. If you look at your home networks, they're all multi-points because you don't have a dedicated link, right, for between, say, sort of your PC and your laptop, you know, between your PC and your printer, between your PC and network drive, and so on and so forth. Okay, but the truth is, deployments are usually in some form of a hybrid format. Yeah, and we'll take a look at that, right? What do I mean by that? So I want to take a look at the actual physical topology. So physical topology just means that what and how cables are connected to allow communication between devices. In particular, we will look at sort of 4 different topologies: the mesh, the star, the bus, and then the ring topology. Okay, let's take a look at them. And the question at the end of the day, right, simply is, what type of physical topology should we use? Okay, so this is a fully connected mesh topology. take a minute and look at that, right? So there are 5 entities on the network, so 5 devices trying to gain access to the network, and they're all interconnected, but they are connected point to point. Okay, full capacity and so on and so on. What can you say about this network? What can you say about it? Is it good or is it bad? What are some of the pros and what are some of the cons? Lots of cables, exactly. And it's not just lots. It's, remember, this is only 5 users here, right? Lots of direct connections. So is it a good thing or a bad thing? Is that a good thing? So I'd like you to sort of talk about whether it's good or is bad, right? Like some of the things that you're writing, like direct connection to each other. Is that a good or a bad thing? They have connections to each other. Is that a good or a bad thing? Is there anything bad about this? Exactly. What are the security issues, Edward? What do you think there might be some security issues with this? If you sort of transfer only, say, if I say, right, this is A, right? Device A communicating with B, right? Point to point, right? This is point to point, so security is good. If I just send down this link, nobody else actually is on the network for me, right? So it's difficult, right, for somebody to sort of look at the data that's going between that's only connected point to point. So actually, this is actually quite secure, but obviously, right? I don't know if you guys picked up that there's actually redundant paths in this network, which means let's assume, right? I'm trying to get to from A, right? This is A here, right? And I'm trying to get to B. Okay, this is B, right? The one on top. Okay. The question is this: is that if this link goes down, okay, if this link goes down, there's an alternate path because I can go from A to C to B, or I can go to A to D, right back to B, or I can go to A to E and then back to B. Does everybody see that? Okay, so if I were to sort of share the sort of pros and cons of such a topology with you, right, is obviously, right, every device has a dedicated point-to-point link, right? The problem with this, right, is this. It is going to be very, very costly, right? And when N, which is the number of users or number of nodes on the network, goes up, right, this may be impractical. But nonetheless, right, you guys listed down a lot of the advantages, right? You have full capacity between any 2 entities. It's very robust because there's a lot of redundancy in it, okay? One link that is cut doesn't affect the communication between 2 other devices, right? And there's great amount of privacy and security because there is a dedicated link, right? And it's very easy to identify fault in such a system because, you know, as long as you can ping between 2 machines, right, the link is up, right? And you can choose, obviously, which particular physical cable to ping across, right? So that's also another benefit. Okay, does everybody see that? So this is a fully connected mesh cable connection. The biggest advantage, right, is the number of cabling required. Okay, I think that was what Chantel and Edward were trying to sort of illustrate a few slides ago. Okay, in general, right, with such a system, you need n times n minus 1 number of cables. So if imagine, right, if there's five of us in this room, right, that's 5, but everybody has to connect 4 different cables, so that's n minus 1. Now, so that's n times n minus 1. But if you have full duplex links, right, and remember, if you recall, full duplex, right, is bidirectional, right? I can divide the number of cables by 2 because I don't need to have a cable from you to me and another cable from me back to you. Does everybody see that? And how we sort of arrive at n times n minus 1? Right? N times n minus 1 is the number of cables we need, right? But divided by 2 if the cables are actually, right, full duplex. Okay, so you connecting to everybody else in the room, and so does everybody else connect to everybody else in the room. So that's n times n minus 1, right? If it's full duplex cable, we simply divide it by 2. Okay? What about this topology? What can you say about this in the same context that we sort of looked at the fully connected mesh network? What can you say about this? Looks more manageable, but why and how? You're absolutely right, but how? Less cables, exactly. What else can you say about this? About fault tolerance, about security? What would be the biggest issues? It's too secure, right? Although there is a central hub that's listening, right? So it's not as secure if you argue, right? But obviously there's a lot less cables, like Lacey said. Okay. Yeah, but Shankai brought up the most important thing. There's a single point of failure. Does everybody see that, right? In the previous sort of star topology, fully connected topology, if one link goes down, there's an alternate path between them. If one entity goes down, which means one of these hosts goes down, that's fine. Everybody else can continue to communicate. In this particular case, right, the biggest problem is this. Yes, there is less cabling as compared to the fully connected mesh, but if the hub goes down, right, the entire network goes down. Does everybody see that? Because everybody's connected to each other through the hub, right? Which is obviously in this case, right, the central controller. So if this central controller goes down, then the entire network comes to a halt in terms of communication. What is the usual course of action to address that single point of failures? What's the usual point of how do we address single point of failures? What can we do if we know that if this hub, yeah, exactly, what we call a redundant hub, right? I could simply, right, include another hub here, and with 4 more cables. So I can use the hub in 2 ways, like what Rana said, right? So it's a failover, which means that if one fails, it automatically switches over to the next hub. Or I could use the dual hub system, and in most cases, that's what is being done, to load balance between the traffic, right, using this network. Okay, so to be very clear, right, even in this top topology, right, it's a point-to-point link. Okay, you cannot communicate between devices, but you have to go through this hub. The advantage of this as compared, right, is obviously there's a lot less cabling, there's a lot less I/O ports. It's also very scalable depending on the number of ports you have on this on your hubs, right? It is essentially quite robust in the sense that yes, your little brothers and sisters could cut one cable, but that does not bring the entire network down. It just brings that one link down. So you might lose one device, but that's okay. Everybody else continues to communicate. Okay, and the other thing from a maintenance, which is why it's so widely deployed, right, in sort of the lab environments, right, is because it's very easy to isolate faults. All I have to go is from the hub to the devices I'm connected to determine if there are any faults between the hub and individual devices. So that's a very easy mechanism to do. But the one sort of catastrophic sort of disadvantage with this, right, is that there is a potential single point of failure, whereby if the hub goes down, the entire network goes down. But obviously the solution, right, the solution is that we can have a failover hub. Okay, awesome. Okay, let's go. Any questions on this? On terms of the, we call it the star because if you fan this out, right, then it looks like a star. Like if you connect them up, down, left, right, it's like a star. Okay, this is your usual Ethernet connection, like in the labs, at home, and so on and so on. This is how you actually connect from a topology point of view. Okay, so this is the bus topology. It's simply a single line that's pulled, right? And anytime you need access, right, you're just tapping off. In fact, if you may or may not be aware, this was the actual, before we went to the hub sort of a setup, this was how Ethernets were actually deployed. This was the Ethernet mechanism. And there are many reasons as to why that is. I'll talk about it. But what can you say about such a link in terms of what we looked at in terms of data rates, security, redundancy, points of failures? What can you say about this network? Anyone? What can you sort of say about this? Exactly. There's still a single point of failure potentially, right? And obviously that's the main cable. Okay. What else? What else can you say about this? Less security, yeah, right? Everybody's listening to everybody else's traffic, right? Okay. Exactly, right? Exactly. Okay. So again, there's pros and cons, right? You start to see now is that in fact, right, in all these real world problems, there is no one solution that fits all the bills. Okay. But let's take a look at this along the lines and formalize what you guys said. First of all, I don't know if anybody realized that this is a multi-point connection. Right? Remember we said we have point-to-point connections and then we have multi-point connections. This is a classic example of a multi-point. Okay. You can imagine, right? This can be deployed. Say if you have ever been to the Burnaby campus. The Burnaby campus is very long, so it goes from sort of it stretches. It's a very narrow campus that goes from that sort of the north-south sort of direction. Okay, it is very probable, right, that there is a bus topology connection, right, within the Burnaby campus that goes from one end of SE42, right, through to the front end, right, in NE1. Okay, and everywhere else, right, you just tap off where you need a communicator. In the early days, Ethernet was deployed this way. All of these taps, we call them the T junctions. Okay, why? Because it's very easy to install. I just have to pull one main cable. Anytime I need to bring another device onto the network, I just splice through it, apply a T junction, right, and then I'm on the network. Okay, there's certainly much less. In fact, the only amount of cabling, right, is that one long sort of cable that goes from the bus, right, that goes from north to south, right, and then everything else is just an individual tap into the network. Okay, but they're obviously so it's very, very cheaper, right, than most of these networks, but also detrimental to this is that there is also a single point of failure, right? This backbone cable can fail. And if it does, then the entire network goes down. Okay. The other thing that is not sort of maybe most obvious to you is actually very difficult to isolate fault in this network, because if I know, right, that two ends cannot communicate, it will take a tremendous amount of effort to try to figure out where the breakage point is. Right? Because I have to go to A first, try A to communicate to B, and then go from A to C, and so on and so forth, and then B to C, and so on and so forth. Okay, so yes, it has a single point of failure, but nothing sort of prohibits us from running a double cable, right? So we can run the cable that goes, front to back, and then so on and so forth. Okay, the one thing, right, that I should mention too is this, and this is maybe not most apparent to all of you now because you haven't sort of been exposed to it, but does everybody see that? Let's assume that this sort of bus cable that we have, right, runs 10 kilometers. Right, and then there's 200 devices on the network. Does everybody see that the amount of time is actually very inconsistent between communication of devices? If I give you the extreme case, right, if I take two devices that are closest to each other, right, the propagation time required for them to communicate is very short, as opposed to the propagation time across the two devices, right, that are furthest away from each other. Does everybody see that? Okay, so that's actually very bad in terms of trying to maintain a consistent quality of service between users, because the average propagation time varies quite widely between devices. So the extreme case is one that are side by side versus the two extreme ends. Okay, the next topology I want to show you is something known as the ring topology. Right, and this in many ways, if you start to take a look at this, right, it's really the bus, but I've connected the two ends. Okay. So this is also, right, a dedicated point-to-point between the two devices, right? And the advantages, like with the bus, is very simple to install. It's very easy to reconfigure because it's, again, another tap into the main cable. But it has a somewhat more simplified fault isolation because you can just now ping to the left and the right of you, right, versus down the path in one way, right? But again, such a topology, right, also has a single point of failure, because any breakage in this ring, again, results, right, in the disabling of the network. But obviously, you can say, well, just like the bus, I can have a dual sort of bus cable system, right? So I have one redundant path. I could do a double ring as well. Okay. But the net effect of this is that of all these topologies that I want to share with you, the key thing that you should take out of this is that none is perfect, right? They all have issues. It's either an issue in cost, or an issue in sort of fault isolation, or an issue with sort of security, right? So in most cases, networks in terms of topologies, which is what I want to expose you to this, is that it's probably of a hybrid nature. So you can imagine, right, in sort of a enterprise network like BCIT's network, right? There's a mix of all of the bus topologies, perhaps for the very long runs between campuses. There are perhaps, right, a fully connected network in the server room, because obviously security is paramount, capacity is paramount, right? But obviously then as we go into the labs, right, what we can have obviously mostly are the star topologies. Okay, so the idea is that you need to sort of at least have a qualitative, meaning a high level understanding, right, of all of the pros and cons of these different types of topologies, so that, right, you're deploying the right mechanism, right, in the sort of the networks. Okay. Any questions on the different topologies? Any questions? Good. Okay, so I'm trying to figure out if we should take, yeah, I think this is a good point to take a break, so that I can go for a longer stretch at the next deck of slides. Okay, so shall we take a break now? Let's do a 10-minute break for now, and then come back. We'll wrap up on this module. Okay. Let me just write that. We'll take a 10-minute break here. Okay, is everybody back? Awesome. Everybody's still doing okay? Right, so today is almost like a nice into summer type of a weather, right? So I don't know how many of you can see the outside world. Have you guys sort of gotten out of the house recently? No. Yeah, I think it's good to be able to go out. Just as long as you maintain all these best practices of what you should do, right? So that would be a good thing, right? Just to get some sun. Biking, that's good. On a trail, Yunbin, are you biking on a trail, or are you just biking on the sort of the bike lanes? Yes, I did take a sip of coffee, if that's what you heard. I got to be a little bit more aware of that. Okay, let's continue. So this is actually now what I want to do with the next deck of slides, right? Is to formalize the 5 layers within the TCP/IP model. Okay, so there's going to be a bit of a discussion on why we actually do the protocol layering, right, and then what these layers effectively do. This, right, just so you know, obviously your quiz today is not for marks, right? It's a mock quiz, right? But this is the gist of your quiz today, right? There'll be a big portion of that's on your quiz. Remember, as I said, that the TCP/IP model is the model that we'll abide by as we move through the entire course. Okay, so I'll show you what I mean by that, and that will filter into a quiz today. Okay, so I want you to pay attention to this because at some point you're going to try to sort of reproduce this information, not the slides, but information, right, for the quiz layer that you have today. Okay. Okay. So remember these two, right? The OSI model. Yeah, so don't worry about the quiz, Chantel, because it's not really for Mark's quiz. It's a mock quiz. In fact, what I'll do is when I get closer to quiz, I'll tell you that today's quiz is actually open book, so you can actually reference material and stuff like that. But I'd like you to do it out of your memory because it's not for marks, right? I want you to just go through the process of the quizzes, and the quiz will very much focus on, obviously, the important stuff from last week that I outlined, as well as I'm reaffirming now, right? So that's what it will be for today, okay? That's right. I'll tell you, it's going to be on. It will be quite focused on sort of the TCP/IP protocol suite. Okay, Chantel. So pay attention for the next few slides, if possible, for everybody. Okay. Does everybody remember this TCP/IP protocol stack, right? Along with sort of the OSI model, right? I want to formalize this to you. So last week, when I sort of introduced to you, right, I did tell you, oh, well, the physical layer deals with sort of the signaling, the data link deals with sort of the MAC addresses, network with IP, right, and so on and so forth. Okay. Remember, right, the communications that we do, as I said, has protocols, right? So we talk about the sender, the receiver, the medium, and the message, but then obviously there's a protocol. The question is, what is this protocol? Okay, and it's actually a lot more involved than you think than for the protocol, say, if X, then Y, right? It's not that. It's actually very, very complex, okay? The fact that we have been able to go from kilobits per second in the last 2 decades to what we have now at a gigabits per second in terms of transmission rates, that's truly enhancements that has been done across all of these layers. So it's not just gains in physical. So sure, there are some more predominant primary and gains in certain layers, but this whole entire 5-layer stack is now layered, right? Since probably the onset of how we do networking and communications, right, to this date, every layer has actually undergone some enhancements over the last 2 decades. And it has brought us from where we were at kilobits per second in terms of transmission rates, right, up to sort of the gigabits per second. And then in the backbone networks, right, they're up in 100 gigabits per second, going to 400 gigabits per second. Okay, so then the question is this: if you recall from last class, why is it that we break this down into different layers? Why? Why not just say that the entire protocol is one layer? Why do we have to say, right? And if you may have remembered, the model that we're focused on is actually just the TCP/IP protocol modularity. Exactly. Why? Why do we want modularity? So you have been exposed to modularity. This is not the first time to be exposed to it, because you've done some object-oriented programming, true? Right? I mean, even in C, you have different functions and so on and so forth, right? I mean, why not just write everything in main? Why do you want exactly? Okay, so the idea is that you have all of these modules because to give you a testament to how robust this sort of TCP/IP protocol suite has been in the last couple of decades is, you guys may have heard of the fact that we went from IPv4 and we're actually using IPv6 now. So IPv6 is no longer something in the future. IPv6 is being deployed as we speak about. Okay, the only layer that changed, right, to go from IPv4 to IPv6, right, was layer 3, the network layer. So essentially, we took out the old layer 3 and swapped in a new layer 3, while maintaining transport and data link without changes. Okay, so the modularity allows us to do that. Now, obviously, right, there has been, as I said, in the last 2 decades, there has been tremendous, right, changes to both the physical, to the data link, to the network, to the transport, and obviously to the application. So it's not just layer 3 being swapped out, but the fact that collectively we've been able to go from kilobits per second to the gigabits per second, right, had all of these different layers changing and evolving over time, right, in some way that is dependent, in some way that's independent. Right, we are independent in the sense of the technology that we progress within each layer, but we're dependent because of the interfaces, right, between the layers. Okay, is that clear? So the question now then is this: do you guys remember the OSI model versus the TCP? So if you look at it, right, the first 4 layers are exactly the same. In fact, the reason I don't dwell too much between the two models is because we only study the physical, the data link, the network, the transport. Okay, across the 2 layers. Okay, if you recall very, very loosely, right, the physical layer deals with signaling. Does anybody remember that? Whether or not we send an analog signal, right, which is a sine wave that we'll start looking at, right, or a digital signal, which is really just different voltage differences. Okay, and then obviously these bits are represented as a signal in the physical layer, right? This physical layer is not the transmission medium, right? It's not the wireless channels, it's not the coaxial cable. That's not that. Those have different status. What we care about is how do we represent, right, a logical 1 as a sine wave, and how do we logical 1 as a digital signal. Okay, but these signals do not have any notion of addressing, which means a signal represented, from a logical 1 to 0 is a signal. The data link layer adds on a type of addressing. Does anybody remember what type of addressing that is? What is the address in the data link layer? Not just the MAC, but the MAC ID. Right? So right now you were on track. Okay. So what that means is this: is now also that the data link layer says this. Okay, you have a signal that sort of the lower layers, but I need to tell you where these signals should be received by. So there will be some to and from address, a source and destination. Okay, but it does a lot more than that, if you recall, because it also deals with error correction and detection. Right? The physical layer is always assumed impaired. So there's some kind of error detection that you actually do along the lines of parity check codes that you guys did in 2725. We'll go a little bit more than that. Okay, but if you have just the physical and the data link layer, in fact, you can communicate within a network because you already have an address, which is the MAC ID, and that is actually true. In fact, if you're on a single broadcast domain like a home network, right, you essentially do not need layer 3, 4, and 5. You just need layers 1 and 2 for communication. So your desktop can communicate with your network drive, can communicate with your printer simply with just layer 1 and 2. Okay. Anybody remember why we need layer 3? What is the purpose of layer 3? In fact, layer 3 is the IP layer, Internet Protocol layer, right? It brings about something that we call IP addresses. Why do we need IP addresses? Why is MAC IDs insufficient? Host to host, what does that mean? How is MAC ID not host to host communication? In fact, right, IP addresses, but the key word here, Jae-Young, right, is across networks. Right? In a single broadcast domain, like your home network, right? I said this, right? Having a MAC ID suffices for two devices to communicate, right? So you have some signals that travels in the wires, right? And then obviously, you also have sort of the MAC IDs to address the different devices on the network. But MAC IDs are not available across networks. In fact, IP addresses are nothing but a logical mapping to the MAC IDs. And it allows us to do something, what Rana said, right, was host-to-host communication, which means I now can communicate across different networks. So from your home network, say, to the BCIT's network, but you don't have a direct link from your home to the BCIT network. You have to go through your service provider, and your service provider, right, depending on where you are, may also have another service provider across jurisdiction, and then finally to BCIT in Burnaby. Okay, so the use of IP addresses, right, is a logical map. And we'll talk about the hierarchicalness of logical addresses and so on and so forth. But this is essentially what it is, right? Is that if you have a network, you can communicate locally using MAC IDs only. But if you want to go across networks, you need to use what is known as routers, right? And then through the process of routing, right, that will get you from source to destination in the most efficient way. Right? And efficient, I'm using it very loosely. It could be the lowest cost, it could be the highest throughput, it could be the lowest latency, and so on and so forth. Okay, so remember, right? Layer 1, layer 2, sufficient to communicate between devices in a single network. Layer 3, which is the IP layer, comes in, right, to allow host-to-host communication across networks. Okay, and the across networks, right, allows you, right, to achieve that because of the process of routing, and hence the devices on the network layers are called routers. Right? The hub sort of topology that we see, right, in the layer 2, they're called switches. So you might have heard about switches, right, versus routers. Okay, so switches are a layer 2 device, right? Routers are a layer 3 device. The difference is this: it's actually you can actually downgrade a router to be a switch. The difference is this: switches essentially is like a USB hub. It connects every device onto the same piece of copper, so you can actually intercommunicate with each other. Right. Layer 3 is also a switch, but it's a smart switch because it now knows how to go from input to output. Right, and choosing which output path to go on to. And this will become more apparent when we go into routing and so on and so forth. Okay, so if by the time that we get to the network layer, we can have now host-to-host communication across networks, then why do we need the transport layer? Yes, but what does that mean? So the keyword is there, process-to-process communication, but what does that mean? No, so protocols goes all the way up to the application. So Yongjin, you have gone one layer too fast. We'll talk about that in a second, but it's not about different ISPs. ISP is nothing but a data path, right? ISP provides you with that data path. Right, the actual exchange of information is through the exchange of messages, and that's achieved through the different protocols like HTTP for web browsing, FTP for file transfers, SMTP. Yes, exactly. The type of data is the protocol. So HTTP for web browsing, FTP for file transfer, right, and so on and so forth. Right. So specifically with what Rana said, I believe I made an example last class, right? And I believe I can't remember who I sort of latched on. But let's assume, right, is Chantel, right? And I said, well, if we look at Chantel's computer right now, right, it's assuming that we're all in class and we're staring at a screen, right? She has one Bongo session going. She has a Learning Hub session going. But I motivated that she has multiple other processes running on her computer, such as some text messaging or some chat sessions going on with her friends to decide what to eat for lunch, right? She's also watching a streaming of a video on Netflix, right, called La La Land, right, and so on and so forth. So the fact that, right, data is coming onto her computer, but she's got different data applications running, which means in this case, right, she's claiming that there's only Bongo and D2L. Obviously, right, data going to the Bongo application should be different than the data actually going to D2L. Does everybody see that? So the ports, right? Remember I talked about the socket, right? IP port pair, right? This is called a socket, right? Identifies the host, and the transport identifies, right, the actual application or process ID that is supposed to receive that on that same device. Right. So it's different protocols. Right. So on your D2L, it's very likely HTTP. Right, and I'm not sure about Bongo. I believe Bongo may use, right, an encapsulated a protocol which is proprietary for themselves. Okay, but let's assume that you have a web browser, right, that's running, right. That will be on HTTP on a certain port, right, and then you could have an FTP session going on. That will be depending on how you're doing FTP, whether it's through a GUI or just on command line, right. That's another port. So there's two streams of data coming to the same IP. Remember, right? Your device, your laptop, has been assigned one IP address. And within this IP address, you're sending data to different applications, right, on that particular host. Okay, so to recap on this, right, the physical and the data link layer allows communication within a single network. The network and transport layer, right, allows for communication, right, across networks. Right, and at the same time, leading on to the correct application that's actually asking for that data. And then the application really, right, at this point in time, right, is the actual protocol that defines the message exchange between the processes. That's correct. So the laptop, right, as what Rana is saying, right, it's been assigned, not the laptop, I should correct that, it's the network adapter. Rana, right? Because you could have multiple network adapters on a laptop. You could have, on some PCs, there are more than one network cards. So the network adapter, right, individually is assigned an IP, and then every application has its own port. Exactly. Precisely, that's what it is. The data is coming in, and depending on whether or not it's encrypted or not encrypted, right, the data can or cannot be seen by other applications. But ideally, right, is that when you're sending data, only the IP should receive it, and only the port should be receiving it. Does that make sense, Shankai? Right? So data is sent out and freely. If you look at all the Wi-Fi access points you have at home, right? And you're not the only individual in your household that's on the networks, not the only device on the network. The data is sent and transmitted over the air on Wi-Fi. The IP address that is assigned to will pick up the data. And then obviously the actual process within that device will pick up the data for display to the end user. Does that make sense? So you're really creating what we call a socket, right? Which is an IP port pair. And that's the basis of any network application. Okay, so IP just means network adapter, right? Process. Okay, so that's how data is exchanged. And then the protocols, right, defines the request response message pairs. Like, for example, in your HTTP, right, you get GET messages. You guys have all done HTTP programming, right? You get some GET messages, and then put messages, for example, right? Get and puts. Okay, is that clear? Any questions on what I just outlined? Because the next slide actually goes into the details of it, but I want to make sure you get the high level. Any questions? No, I just said this, right? So remember, I said layer 1, layer 2, L1, L2 allows you to communicate within a single broadcast domain. L3, L4, right, is your IP port pair, right? And then L5, right, is the protocols, which is the request response message pairs. Like, so if I give an example, HTTP, right, there are GET messages, there are PUT messages. That's your request response. So if I say GET, right, index.htm, right, from hostname learn.bcit.ca, right, get this file, then the PUT will be obviously, right, to give you the data that you have requested for. Okay, Rana? Okay, so then the next slide, right, really just is the key takeaway that I summarized everything that I've just talked about. Okay, so the physical layer, right, you should be aware that it actually deals with what is known as bit representation, right? Essentially, right, is trying to coordinate how you transmit a bit of information. And I'll say this: the entity that we deal with in the physical layer is a bit, single bits. What's a 1 and what's a 0? The physical layer, if I can sort of highlight to you, right, is not the actual physical transmission mediums. Those have other standards like twisted pairs, coaxial cables. They have different sort of standards that defines what the cable should be. We don't care about that. We care about the coordination to represent a bit as a signal for transmission. Okay. The data link layer now has obviously some kind of addressing that I've said, right, known as the MAC ID. Okay, but because I now have a destination, I am unlikely going to be transmit a single bit of information. Can you imagine, right? If I'm transmitting 1 terabytes of data, and I'm addressing every single bit, which means, right, MAC IDs. I don't know if you guys are aware, but MAC IDs are 48 bits. MAC IDs are 48 bits. Do you think it is likely that I'm going to add 48 bits of addressing? In fact, I need to add 96 because to and from to every single data bit that I'm going to transmit across a network. Would that be efficient? Which means I need to carry 96 bits of addressing for every data bit. Is that efficient? No, obviously. So what data link does is that because I'm putting on a header, okay, effectively, I'm going to put a collection of bits together in Ethernet, right? The amount of data can be anywhere from 50 bytes to 1,500 bytes. So that's what we call a frame. And that's the entity that layer 2 deals with. I deal with more than just a single bit of information. I'm putting some headers to it, okay? In addition, right, as I said, because the physical layer is assumed impaired, right? I believe I did this demo with you guys, right? Last week. If I unmute everybody now, okay? And I hope you guys are noisy. Well, you guys are too quiet. But if you guys are really noisy in the background, okay, because most of you are in listen-only mode today, I think, okay? But if you guys are really, really noisy in the background, then what happens is that, right, there's going to be a lot of background noise. And that would be an impairment, right? We'll study that next week, right? To the signal, which is me, the information I'm trying to deliver over the lecture. Okay, but in any case, we'll look at the ideas of how we do framing. We'll look at the ideas of how we do error detection, right? And then one thing is how do we share, which is what is called the medium access control. Okay, so that's a lot of things. Layer 2 is actually one of, every layer is very important, but layer 2 actually does quite a lot of work because it needs to provide a service to correct the issues by the physical layer, and then it needs to support layer 3 as well. And then obviously, right, the moment we get to sort of the network layer, which is layer 3, right, we deal with the transmissions of a packet. So this is the most common notion of IP packets. Okay, the book uses a word called datagrams. Datagram is just an old English word for packets, right? So datagrams really refers to packet. Okay, like in the old days, right? There are telegrams, and so this old English, right, that is used to describe, but really datagram is a packet. Okay, what we want to achieve in layer 3 is what we call host-to-host communication, right? Network adapter to network adapter, and we achieve that right through the process of routing. Okay, layer 4, as I said, right, a few minutes ago, allows for you now to achieve process to process, right, which means application to application. So, i.e., web browser server, web server to web browser, right? YouTube server to YouTube client, right? That's what I mean by process to process. Okay. There are two ways of achieving that, right? I did not want to complicate sort of the technologies, but there's a reliable way of doing it called TCP, and there's an unreliable, what we call a best effort, right, which is called UDP. The difference is the amount of resources that are required. So if anybody heard of denial of service attacks, and anybody heard of things called DOS, or even DDoS, right? There's it's actually a exploit on TCP, because we'll see TCP many weeks down the road, maybe in about 5 or 6 or 7 weeks later. But essentially, if you do TCP, right, which is a reliable service, it requires resources like memory, CPU cycles, right, and so on and so forth. Okay. Effectively, you can say this: I'm going to now connect to a server, and I'm going to request for 100,000 TCP connections. Okay, and the web server will continue to enable these processes, but it's going to now use up all of its memory, and it's going to use up all of its CPU cycles to maintain the states of TCP, where effectively it cannot service out any real data, right? That's essentially what a denial of service attack is. Yeah, but we'll deal with that later. There's a lightweight version of it, protocol. Okay, it's called UDP, but it's non-reliable. Okay, but we'll leave that for now. For now, what you should be aware of, right, is that there is a TCP, which is reliable, UDP, which is non-reliable, but the primary purpose of the transport, right, is actually for process to process, which means port to port. Okay, and then last but not least, right, the application that has been motivating is not the GUIs, right? So layer 5 is not, right, the browsers, right? Layer 5 is HTTP. It's the actual protocol. We're looking at what we call data communications. Any questions? So you need to know the 5 layers: physical, data link, network, transport, application. You need to know the type of entities that it deals with: a bit, a frame, a packet, either a segment or user datagram, right? And that's what I really want you to be able to get out of this in terms of a high level of understanding. Today, we'll go and start with the physical layer. We'll spend about 2 to 3 weeks on the physical layer. And traditionally, the 2 to 3 weeks is the harder part for most students in this course. And then once we get through the physical, right, everything becomes a lot easier because it now gets closer and closer to what you do from a programming level. Okay, any questions on that? Okay, so if there are no questions, let's take a look at this in action. Okay, so remember, right, we said this. We need protocols because we want to have efficient communication and we want to have interoperability. Okay, throughout this whole course, right, you should always reside, right, the 5 layers in your mind, right? In fact, one of the best ways actually to remember this, and this 5 layers is, as I said, is the classic interview question. Right? Somebody will just come in here. What's the network layer do? Why do you have to have the network layer? What's the transport layer do? And so on and so forth. The best way to sort of understand this is, as we proceed with the course, put yourself in a context to be a text message. And every morning when you wake up, just refresh in your mind what happens to a text message that is being sent at the sender, and how is it that is being received at the receiver through this 5-layer protocol stack. Okay, if you can do that, right, very soon, right, all of this will become very clear to you without any memorization, right? And my goal is to decipher each of these functions across the 5 layers over the next remaining 11 weeks, right? And step you through it, okay? So the reason why we layer sort of this protocol is because we want to reduce and modularize the functions. And in this case, right, the rules for the sender receiver, right, to communicate. And I said this effectively. I don't really need to have this, but because I'm dealing with trillions of packets on a daily basis, right, I need this communication to be very effective. And because I want to have interoperability different than different manufacturers, I need to have some standards. Okay. Now, as we decipher through all these 5 layers, you'll find that the functions that are provided within each of these 5 layers is actually extremely complex. Right? The physical layer, the fact that we have to spend 2 to 3 weeks on it, right, indicates how complex this layer is. In fact, we only scratched the surface of it. Right? There are individuals who spend their entire lifetime looking at the physical layer on how to do better and to achieve higher data rates and lower latency. Okay? I'll only give you sort of a very high-level introduction with enough depth understanding to understand how everything gets transmitted. Okay, so we sort of break them down into different layers, right? And I want to show you example now of what it means with this layered approach. So this diagram here, if you can follow me here, right? There are 3 sort of entities here, right? In terms of end users, A, B, and C. Okay, in fact, there are 3 networks here, because you'll see that there's one router here in the middle. Okay, so this is network 1. This is network 2. Right, and then this is network 3. Okay, oops, sorry, I clicked on the wrong mouse. Sorry about that. So I clicked on the mouse. So you'll see that how we see that is because across routers, right, is where we bridge into another network. Within each network, right, there's usually a link device, and this is what we call a switch. The switch is really nothing like a USB hub. It essentially states is I could have users A, A1, A2, A3, A4 within network 1. And I'm going to connect everybody onto the same key piece of copper, right, through a switch, so that everybody can communicate with each other. It could be wireless, it could be wired. It doesn't really matter, right? The notion of a switch is simply that everybody can see everybody else on a network. To communicate across different networks, I need to go through a layer 3 device, right, which is called a router. And again, once I get into network 2, right, or network 2, I could have another switch here with many B1, B2, B3, B4, B5s, and then the same as for C. Okay, but what I want to sort of show you is this. If we now focus only on the communication between A through to B, so A as a device wants to communicate through a router to communicate with B, I want you to put into context what the protocol stack looks like across the entire network, right? I'm going to show that to you. It looks like this. Take for a minute. Just take a look at a minute. Why is it that at different devices on the network, there's a different depth in terms of the protocol stack? Take a minute and look at this and tell me what you observe. What do you observe? What is most striking to you in this terms of the diagram, right? So I'm saying this, right? At the source, right, which is user A, right, there's 5 layers. At the receiver, which is the destination, there's also 5 layers. I'm not sure what you mean by linear, but maybe I think you're trying to, maybe you might want to say symmetry. Is that what it is? Or what do you mean by linear? Yeah, I would think so, because you'll notice a couple of things, right? It's symmetric, right down the middle. Okay. The fact is this: is that what I really wanted you to have picked up, right? Yes, it's symmetrical, right? You'll see that obviously, right, with protocols. Exactly, you don't need all 5 layers. Right? In fact, you will notice that throughout the entire network of communication, only the end entities, which means A and B, the source and destination, goes through the entire 5-layer protocol stack. Right? Because you start to see, right, only the layers at the source and entities at the receiver cares about the actual data. Everything else, like the switches, everything else like the routers, it doesn't really care what payload you carry. It doesn't care. It doesn't care that you're transmitting the picture of your best friend or the picture of your dog or the picture of your cat. It doesn't care about what the actual payload is. It doesn't care about the messages. It only wants to get you, based on this function, across a single network as in the switch, or across networks as in the router. And it only looks up to the layer that it cares for. So in terms of the n entities, A and B, right, source and destination, they need to encapsulate the data and they need to decapsulate the data. What I mean is the actual information content, like the picture of a cat they transmit. A switch essentially does not care about what you carry. In fact, it doesn't even care about the IP addresses because all it needs to do is to get you from MAC address to MAC address. So you'll see here as a switch, right? It does only link you from network adapter to network adapter. Where then you get to a router, because it's a layer 3 device, right? It will obviously need to get you to the IP layer. And then once you're into another local broadcast domain, only the switch comes into play, and then the destination device extracts the information. Does everybody see that? Right? Along the lines of what Shankai said. Every network entity only deals with what it needs to deal with. That's what modularization is all about. Okay? But there's another thing that I would have hoped that you picked up. Right, so that's sort of all the switches and routers. Do you see that in this particular diagram at the router? So to highlight that, right, if you look at the switch here, the receiving and the sending is shown as one entity. Does everybody see that? Right, so the data link across the receiving end and the sending end is one entity. But the moment you hit a router, the physical and the data link layers from the receiving end and the transmitting end, they are shown as two separate blocks, which means separate entities. The question is why? What do you think that so this is not a typo. This is not an error in the diagram. Why do you think that is the case? Different networks. What does that mean, Rana? Can you be a little bit more specific? Can you go a little deeper? Not that it has to no, but so it's not what Shankai said, because obviously, right, this switch here is also doing receiving and sending, right? This switch here. Why is it that at the router, this receiving and this sending is shown as two separate entities? So Rana's on the right track, but can you be a little bit more specific than just different networks? No. So you have different MAC IDs, right? For a switch, you also have different MAC IDs. But you're absolutely right, it could be different networks. But why? Why is it that a different network will require us to maybe have a different physical and data link layer? So remember, right? I said that this network that A is on, this is one network. Yes, could be different protocols. What does that mean? What type of protocols? Because obviously, right, let's assume this is web browsing. The term that we use as protocol is HTTP, right? That's application to application. You're getting closer, but the choice of word is wrong. So it's not about protocols, but different what, though? It's different something. Anybody else? No, not process. Process is a layer 4 sort of term. Different data stream. What do you mean, Jason? Remember, right? All of these entities, with the exception of the source and destination, really doesn't care about the content. Right? It shouldn't. I don't really. If I'm a router, I don't care if you're transmitting an image of a dog or a cat. That's not for me to judge. Different MAC IDs, true. But so between here is different MAC IDs too. Right? Within the switch, it's the same thing. We do still have 2 hours and 15 minutes left in the class, but I don't think we should spend 2 hours and 15 minutes on this. Someone. So let's go back to what Rana said before. Right? Her very first intuition, right, that she said was that it was, I'm trying to find her message here now. She said something that was very close to the answer. Different networks. Okay. Let me ask you, who's on a Wi-Fi network right now? Who's connected to the internet through Wi-Fi? Right? I'm sure most of you are, okay? So what happens after your connection through Wi-Fi? Ethernet's great too. What happens? For those that are on Wi-Fi through some access wireless routers that you guys have, what happens after Wi-Fi? Exactly. Okay? So you start to see now, right? Most likely, in most use case, right? You're going to have Wi-Fi as your last mile, which means to the consumer, to your laptops, right? Your mobile devices. And then behind your Wi-Fi, because you're going to your wireless access point, right? There should be a cable. And usually, right, that cable will be running on Ethernet. Right? So your RJ45s, right, connected to your Ethernet cables, Cat5 cables, and so on and so forth. Right? And then from your Ethernet, you might go on to depending on who your service provider is, right? It could be fiber optic and so on and so forth. Does everybody see what I'm trying to illustrate here? Is that along the transmission of data, there could be a change in the physical layer technology. Wi-Fi is wireless. It's a sine wave. But the moment you go onto Ethernet, that's on a cable, like a Cat5 cable. That's digital signal. So the idea behind this is very simple, right? And this is not even a typo, right? So for some students may come back and say, oh, this is a typo. No, it's not. Because on your single networks, right, you're likely connected on the same technology, right? Your Wi-Fi's and so on and so forth, okay, between you and the switch. But when you go across network, let's assume that you're trying to transmit data, right, from your home network to the BCIT network. You very likely will start out using Wi-Fi or Ethernet at home. But at some point, when you hit your service provider, there's some fiber optic links that can go on. And then you could have some Ethernet that goes on upon reaching and entering to BCIT's network. And then obviously, right, right, it could go out to Wi-Fi again. So the router, because it's going across networks, will show you that you have a common IP layer. But it allows for you, right, to have a different physical and data link layer. So what I'm trying to say is this, is that in 802.3, right, you have Ethernet frames, right? And obviously, right, in 802.11, which is Wi-Fi, right, you have Wi-Fi frames. The framing structure between Ethernet and Wi-Fi is very different, okay? Which do you think is more reliable, Ethernet frames or Wi-Fi frames? What I mean by more reliable is which would likely require less retransmissions. Exactly. Okay, obviously. So which means, right, Wi-Fi frames are created with the possibility of a higher probability of retransmission, which means that the Wi-Fi frames are usually slightly smaller in sizes. Whereas Ethernet frames can carry more payload because the chances of having retransmission on Ethernet is lower. And because the routers allows you to cross between two networks, right? And hence, right, could potentially be two different, it could be the same, but potentially be two different types of networks. And hence it's shown as two different entities. Is that clear? Okay, I just want to illustrate this because in the previous year, student has brought this up as a question, you know, as to whether or not this is actually a typo, but it's really not. Okay, it's taking at the level of a router the ability, right, to go from a different network such as Wi-Fi to Ethernet or Ethernet to fiber optics or any other conversion between the networks. Okay, Any questions on that? So just to wrap up on this deck of slides, right, everything else is very simple in here, right, is that there are now two principles for us, right, when we want to do protocol layering, okay? The first one is very, very intuitive, right? We need to have, if we want to have bi-directional communication, then we need to be able to do the opposite task. So if one layer can do sending, one layer should also do receiving, and one layer is doing encryption, the same layer should be able to do decryption. But in more formal way, right, the types of entities that we deal with, right, in terms of the objects must be the same. Okay, so what that means is this, right? In the sender, if I send out bits in layer 1, then I must receive bits in layer 1 at the receiver. If I send out frames, then I should receive frames. If I send out packets, I should receive packets, and so on and so forth. Okay, so it must be able to do send and receive like equal and opposite tasks, right? And I should deal with the same entity. But the other thing that I want to highlight out of these 5 layers, right, is to differentiate between what we call a physical connection and a logical connection. So if I go back to this diagram here, right, the physical layer deals with the physical layer at the sender and the receiver. The data link deals with the data link, right, at the sender and the receiver, and so on and so forth. Do you think these connections here, are they logical or are they physical connections? Logical, exactly. Does everybody get that? A physical just means that there's an actual wire that connects the physical layer to the physical layer. There's an actual wire that connects data link to the data link. There's an actual wire. There's none of that. Okay, what I'm trying to say is that all this is actually accomplished through the process of encapsulation. You're actually putting data together into a stream of ones and zeros at the signal. All of these are actual logical connections. There is no physical wire that connects the physical layer to the physical layer of the TCP/IP. There's no wire that connects the data link to the data link. Okay, so all of these are all logical connections, which means layer 5 to layer 5 communication is an abstract sort of communication, right? It's where the bit locations are in transmission of the database. They're all logical. There's no actual wiring that connects layer 5 to layer 5, layer 4 to layer 4, and so on and so forth. What you do need to know is that between the layers of 3 and up, so your network, your transport, and then the application, right? They're what we call end-to-end connections. The physical and the data link, they're called hop-to-hop. And they're hop-to-hop really, right? Because, as I said in my previous diagram, is that the physical layer can change from one link to the next. So on this guy here, right, this switch, right, could be dealing with Ethernet type of information, okay? And then this could be dealing with Wi-Fi, for example, okay? And as such, it's hop-to-hop interconnection. So you'll start to notice one thing very quickly. Physical and data link are usually paired together. If there's a change to the physical, there will be a change to the data link, right? Because if I have Ethernet, I'm going to have Ethernet frames. If I have Wi-Fi, which is wireless, then I'm going to have Wi-Fi frames. Okay, so the idea in terms of sort of connections, they're all logical, right? There's no physical connections here. The physical connection that we have are actually the cables, but there's none of that here. The 5 layers operate on a very logical type of connection, where the first 2 layers, right, are truly just hop to hop, and the higher 3 layers are end-to-end, which means, right, the payload that's carried in the network layer is not extracted or changed in any way or form by the routers. It's just a pass-through, right? And then so is the transport, and so is the application. Is that clear from a sort of a framework point of view? That in these layers, right, we have layers 1 through to 5. Each of these layers, right, is modularized to perform this task. Layer 1 and layer 2 are highly coupled together, because anytime there's a physical layer change, there is likely going to be a framing change. Okay, they're all logical connections, right? But the first 2 layers, because there's a potential for a frame change based on the change in physical layer, layer 1 and layer 2 are what we call hop to hop. But anything higher, layers 3, 4, and 5, are only dealt with at the source and destination, right? With the router just being a pass-through. They are what we call end-to-end logical connections. Any questions on that? Okay, please stop me if there are any, right? And then last but not least, right, I want to show you the process of what it really means in terms of encapsulation versus decapsulation, right? So if you look at the diagram here on the left, right, essentially, let's assume that I have a web client, right, and a web server. I'm going to send a request message, right, which means the payload. Request message of HTTP would be like get index.htm from hostname learn.bcit.ca. For example, that's the message, right? So that's my get message. So I started with the application generated by the web browser. Then I go to my transport layer, which gives me minimally this addition here, this number 4 here is a header. I'm adding a header to it, which includes the port numbers from source to destination. Then I go down to the network, which I'm going to add on the IP addresses. Then I go down to layer 2, right, which I'm going to add on the MAC IDs. And then obviously the physical layer just converts this stream of ones and zeros into the appropriate analog or digital signal. That gets transmitted in my network until I hit a router. And then depending on sort of the routing that is being done, the router would look at the layer 3 header because it needs to know which host to host, which is defined by your IP addresses, it needs to send to. So it will decapsulate the physical layer to the frames and then extract layer 3 header information that it requires, because that's what the router is, a layer 3 device. Extract the source and destination IP, and then re-encapsulate again, right? Because it needs to tag on the appropriate frame header. So this could be Ethernet, this could be Wi-Fi. So it takes all of these data, reframes it into now a Wi-Fi frame, and then goes onto an analog signal all the way to the destination, where now the contents, right? Remember, the message was get index.htm, host name, learn.bcit.ca. At the receiver, it needs to figure out what the MAC ID is, because it needs to go to the appropriate hardware. It needs to figure out which IP, which host. It needs to figure out which port, right? So it's assuming that this is for port 80, right, at the web server. And then finally, right, it extracts the messages, right, and then is sent, obviously, and used by the appropriate process within the receiver. Does everybody follow this, right? So this process is what we call encapsulation, right? If you're adding headers, it's called encapsulation. If you're removing headers, it's called decapsulation. And then there's another encapsulation because you might change the technology to do that, right? So you're on Ethernet and then you're going to Wi-Fi, for example. And then obviously, right, at the end entity, which is your receiver, you decapsulate again. So this encapsulation, decapsulation process happens every time you go from one hop to the next hop to the next hop, right, until you get to your destination. Quite complex, huh? In terms of what it does. But the headers really, right, for now, you just have to think of the headers, right, containing the right and pertinent information, right, for this communication to actually work. Okay. Any questions on that? Okay, and then this very last slide is a summary of sort of the terminologies. Okay, if you look at this one slide that I have here, right, in terms of the entity names, right, from the physical layer, we call them a bit. Data link, we call it a frame. Layer 3, we call it packets. The book calls it datagram, but as I said, datagram is just old English for packets. Layer 4, if you're using TCP, it's a segment. If you're using UDP, it's user datagram. And then obviously, right, at layer 5 is the message. From a addressing point of view, right, you have your link layer address, which is your MAC ID. You have your logical address at layer 3, which is IP. You have your port numbers, right, which, for example, on the server side, right, HTTP is on port 80. And of course, you have the names, which obviously are URLs, and depending on the type of addresses that you have at layer 5. Okay. Are there any questions at all here? Okay. So if there are no questions, then let's try to see if we can do a mock quiz today. Okay. So I want you to treat this as a real quiz. Okay. Just do the best you can. You don't have to sort of be spending a lot of the time in terms of what you have to get it right and so on and so forth, right? This is really more of a process thing that I want to do with you today. Okay. So let me get up the quiz. Okay. And I'll run through the process with you again very quickly. Let me just load up the quiz for here. Okay, so next week we'll have a real quiz, right? But this week's quiz is still just a mock-up. I just want to share the screen with you. Okay, so remember what we discussed last week, right? Is that what you will see, right, in terms of your quiz, right, is that you will have the content, right? Every week I'm going to load up for you, and then you'll see in the lab material, right, in this case, right, there's going to be page 1. Okay, so if you click on it, right, it just simply says this. Oh, okay, it's a lab exercise, okay? So I've updated the instructions a little bit based on the feedback that I got from you last week, right? So this quiz will be say 10 marks total, okay? But it's not for marks today. It's just do the best you can, okay? I want you to do it the best you can, right? I mean, however much you can actually remember. Then I'll tell you, okay, the total quiz will run for 25 minutes, okay? But again, today we'll keep to the 25 minutes, okay? But that includes obviously the submission time and so forth. What I've done is this, is that I've allowed now you to say that, okay, I can upload both either a JPEG or a PDF. That's fine. Okay, where you will do the upload after you're done with the quiz is to take a picture of what you wrote, right, and submit it into the folder quiz 2. Okay, and make sure that you write your name and your student number on the submission, right? That's the only one thing that I want you to do, right? Make sure you have your name and your student number. But bear in mind, you're only allowed one submission. Okay, so you can do multiple files, but you can only submit once. Okay, so I want to run this process with you today, right? And then any glitches will work it out. So at the end of the day, right, I want you to try the quiz for today as if it was a real quiz, okay? As much as you can. It's not for marks, but really just to run through the process, okay? So where do you submit it? Well, you go to activities and then you find assignments. In here, you will see that I've created 2 tabs, right? So right now, I'm going to now enable this folder. So I'm going to make it visible to you. Right, and I haven't sort of opened up the timing yet, but I will do the timing as we start. Right, so I know that the quiz, as I said today, will run for 25 minutes. Depending on what time we start, right, I can change sort of the due time as we get started. Are there any questions? So essentially, what you should do now is take out a piece of paper, right, write your name and not username, your name and your ID on A00. Is everybody following? Right, and then obviously you submit it to quiz 2 when you're done.
So can we, for example, upload a zipped folder if we have more than one document?
No, so no, don't. So either do a PDF or a JPEG, because I'm going to grade it right on the document itself, like your submission.
Okay.
It takes too long, and I don't want you, because remember, right, you only have 3 minutes to turn it around, and it's okay if you cannot submit. Just do your best. D12 locks the time, so I want to see what's the minimum amount of time that you guys would require. Do you understand what I'm saying? So
Yep.
Don't worry about it. Just do the process and do it. It's not for marks, right? And do the best you can on the quiz, right? Let's just do your best. Again, I said it's not for marks. I want to just really run the process with you.
Sounds good.
Yes, I want you guys to do the quiz now, right? So once we're done with quiz, you guys can take a break. Okay? So let's just try it. It's just a mock quiz. It's not for marks, right? I want you to run it so that you are not sort of shocked by it, and then we can even better this process for next week. Okay? Okay, William, are you guys ready with a pen and pencil? Pen and pencil, no. A paper, like you guys need a paper, right? So take a minute, right? Take a breather. Again, it's not for marks, right? We're just trialing this process, okay? So do you guys see the quiz that I've flashed on the desktop, like on the share screen?
Yes.
Okay. So so I'll wait to 11:05 so that the timing is a lot. Yeah, pencil's fine. Just paper and pencil. Okay, we'll start at 11:05 so that time is easy to sort of manage from that way. Okay, so you guys have a minute or two to get started, right? You guys can see the time there, right? Can you guys see the time?
Yes.
Yeah, pencil's fine, okay? So because it's a mock, right? We'll just wait for another 15 or so seconds, right? As I said, right, there are a couple of questions that you will do, okay? And you don't worry about it, right? You shouldn't go back to the previous question anyway. So I'll give you ample time to do each question. And then every fixed amount of time, we'll move on to the next question and next question. At the end of it, you have 3 minutes to take a picture of your JPEGs or convert it to PDF, which is preferred, right? So this is what I would prefer you to be able to do, right? Either a PDF, right, single, or multiple JPEGs, that's fine. Okay, and where you submitted this quiz to, and I'll monitor real time to see the amount of time you guys need to do so. Okay, so we'll start the quiz at 11:05, right? And then obviously it will stop at 11:30, right? But it will be flash question by question. Okay. So question 1, right? The stop time will be, okay, so it's 11:05 now. So let's assume the quiz is starting, okay? And relax, okay? Just do the best you can, okay? It's not about the marks today, okay? So I'm going to flash to you the question now. I say, okay, this question is for 5 marks, and you're going to get 11 minutes. You can read the question, right? The TCP protocol is a layered framework for the design of network systems, okay? And I said this. In the table below, right, and I'm going to flash to you the table. Does everybody see that?
Yes.
Okay. All I want you to do now is this. I want you to fill in layer 1, layer 2, layer 3, layer 4, layer 5. What is the name, right? So ideally, you'll start a physical layer and up. Between the functions, the packet names, and the addresses, I want you to fill in one of these items in blue. Does that make sense?
Again, after the layers, what should we do?
So the functions, the packet name, and the addresses, I want you to fill in an entry from one of these items in blue.
Okay.
Okay, so you have 11 minutes to do that, right? We'll stop at, for this question, 11:16. And then if you have any questions, feel free to type as a private message to me like you would do in class, right? Just raise your hand. Again, as I said, it's not for much. Just do the best you can. If you have any questions, just type on private, send me a private message. There are no restrictions, right? In terms of what goes in the box, how many, and so what I mean is that on purpose, you realize that some boxes may have more than one entries, some boxes may have no entries based on the ones I provided. So it's not an elimination type of an exercise, right? You need to know which goes into which box. So let me say this, right? To answer Edward's question, there could be some boxes with multiple entries, and there could be some boxes with no entries at all. Okay, Edward? No, I don't want you to solve it by process of elimination. That's okay, Chantel, right? This is just a mock quiz. That's okay. Don't worry about it. No, there's another question. So it's coming. So I'm waiting for 11:16, and then I'll move on to the next question. So I've given you plenty of time. So I've given you more time than I think it's necessary, just obviously because I cannot keep pace of everybody's working speed. Okay. So that's coming up in a few minutes, maybe a minute here. Okay, so it's 11:16 now. I'm going to move on to second question. Okay. So you also get 11 minutes. So you stop this at 11:27.